Hello, and welcome to Foundations of Advanced Math. This course is about finding and communicating valid logical arguments about mathematical topics and concepts. Our first course goals will be to study collections of sentences called logical arguments and determine whether or not they are valid. Let's start with some simple examples where the subject matter is not mathematical, but where our life experience might support our ability to determine whether or not an argument is valid. All right, so here are two examples of arguments, and we'll determine whether or not each one of them is a valid argument. So the first argument is, a car will not run without gas. I don't have any gas in my car, therefore my car will not run. So this particular argument is called valid because the conclusion that my car will not run necessarily follows from the premises that a car will not run without gas and I don't have any gas in my car. So that conclusion follows from not having any gas in my car. I'm assuming this is a car that takes gas, and assuming that that car will not run without gas. So that first example is a valid argument. The second example is a little bit different. A car will not run without gas. My car does not run. Thus, I must be out of gas. My car does not run doesn't necessarily imply that I don't have any gas in my car. Maybe my car doesn't run because the engine's broken. So the conclusion that I must be out of gas does not necessarily follow from the fact that my car does not run and a car will not run without gas, because there might be other reasons why my car doesn't run. So if you can hear from the way that I've explained these two examples, that the first one is valid and the second one is not valid, then that's the type of idea for understanding logical arguments and valid arguments in particular that we're going to develop over the course. So if those two examples were still kind of tricky in your mind, don't worry at all. We're going to go over lots more examples. All right, so let's transition to some definitions that are going to help us decode complex arguments and help us determine whether or not those arguments are valid. All right, so the first word I want to define is the word statement. A statement is anything we can say, write, or otherwise express that is either true or false. And so I have a list of 4 items, and I want us to walk through and determine which are statements and which are not statements. So the first one is, it is raining inside Omar's house. That is a statement. It is either true or false that it is raining inside Omar's house. And for Omar's sake, I kind of hope that that statement is false. I don't want it to be raining inside his house. The second example, a squared plus b squared equals c squared. That kind of sounds familiar. Have you heard of the Pythagorean theorem? Yes, well, it is an equation, but the Pythagorean theorem actually says that if A and B are two sides of a right triangle and C is the hypotenuse, then A squared plus B squared equals C squared. But as number 2 is written, it's not clear what A and B are. And are they numbers? What kind of numbers are they? Are they the lengths of a triangle or just random numbers? I don't know. So number 2 actually isn't a statement because I have to have more information about A and B and C and what those numbers are and where they're coming from to be able to determine the truth or falsity of that equation. Item 3, is the light on? That is a question, so it's not necessarily a statement. Commands are also not statements. If I were to say, please turn the light on, that would not be a statement. That would be a request. So 2 and 3 of these 4 examples so far have issues. Number 4, Ben's pizza is delicious. Yep, that's a statement because his pizza is either delicious or it's not delicious. And so number 4 and number 1 are the 2 statements. All right. So statements just by themselves can be kind of boring, but we can create new statements, compound statements from simple statements, and that's what we're going to do next. So our first compound statement is called a conjunction. So P and Q are going to be two simpler statements, and I'm going to put them together with the word and, P and Q, and it's denoted with that funny looking upside down V symbol. It kind of looks like an A for and, but it doesn't have the crossbar in the A. So P and Q is the statement that is true when both P and Q are true, and otherwise it's false. So over on the right-hand side of the screen, you'll see what's called a truth table, and it tells you about the truth or falsity in that third column of the compound conjunction statement, depending upon the truth and falsity of the statements P and Q. And so in that first row of the truth table, the T underneath the P and the T underneath the Q are indicating that P and Q are true, which leads to the conclusion that P and Q is also true, because the true here for the conjunction, is indicating that this compound statement, this conjunction is true when both of the component statements P and Q are true, and then it's false otherwise in the three remaining rows of the truth table. So let's look at an example. All right, so here's some examples and a non-example. All right, so some frogs are green and some grass is green. So the two component pieces of this conjunction are some frogs are green, that's the P, and some grass is green, that's the Q. So I'm pretty sure I've seen green frogs before, so I think that some frogs are green is true, and some grass is green. I'm looking at the grass in my backyard and it's green today. So I think that the some grass is green is also true. So this particular item 1 as a conjunction happens to be true because the two component pieces P and Q are true, are both true. The second sentence is just a condensing of the first sentence. So some frogs and some grass is green. So this is something that we do in the English language. We combine things and make them shorter and more concise. And so statement 2 is an example of taking statement 1 and just rewriting it in a way that's just maybe less repetitive. All right. The third one is a warning statement. Ron and Hermione are married. So that is, looks at first glance like it might be a statement, but it's a little bit ambiguous. And in mathematical writing in this course and in the law and other instances, if a sentence is can be interpreted in two different ways, then it should probably be rewritten. And the Ron and Hermione are married sentence can be interpreted two ways. So that could be a condensing of Ron is married and Hermione is married, as 2 was condensing the sentence, the statement from 1. Or sentence 3 could be that Ron and Hermione are married to each other. And if that's what the writer intends to convey, they need to write the to each other part at the end of that sentence. Ron and Hermione are married to each other. Otherwise, we could get confused and think that this is saying that Ron is married and Hermione is married. All right, the fourth sentence here. From the equation above, 3x is less than 12 and x is less than 4. All right, so what's happening from before the and to after the and is some algebra has been performed. 3 is, the inequality is being divided both sides by 3. And that's how we're getting x is less than 4. So really what's happening with this x being less than 4 is that this and is a conclusion. The x is less than 4 is a conclusion being made from the 3x being less than 12. So this particular and is not a conjunction. It could be replaced with thus instead, but we're going to reserve the word and for the mathematical and that's defined by this truth table definition. And so in this class, we're not going to use the word and in sentences in this way in item 4. All right, so that's our first compound statement called a conjunction, and it's basically just using the word and between two component statements. All right, next compound statement is called a disjunction. And instead of the word and, we're going to use the word or. So the disjunction of P and Q denoted P with a V symbol, Q. That V symbol is pronounced or. P or Q is the statement that is true if either P is true or Q is true, or both happens to be true, and is false otherwise. So that's what's being conveyed over here in this truth table. In this first row of the truth table, we have that P is true, Q is also true, and the or, the disjunction is true in this case, according to the definition. And in the second row of the truth table, we have that P is true, but Q is false. But the disjunction, the or statement, P or Q, is still true because one of the two components is true. Similarly, if P is false, Q is true. The disjunction P or Q is true because Q is true. And if P and Q are both false, that's the instance where the disjunction is false as well. Excuse me. All right, let's look at some examples. So, it is raining, or all the strawberries are red. Okay, so it is raining is a statement. That's our P. That's either Q. I mean, that's either true or false. And all the strawberries are red. That is also a statement. Either all the strawberries are red or one of the strawberries is not red. So that's true or it's false. The second is a warning. The second statement here is a warning. Jamal will eat soup or salad with his meal. So I've worked as a waitress before, and I asked people, would you like soup or salad with your meal? And when I'm asking them that, it is implied in most restaurants at least, that the person gets to choose one, either soup or salad. But if this is a mathematical definition of or, then it could be the case that Jamal could rightfully reply, yes, I'll have both. So the word or in the mathematical sense, the or statement is true if both of the component statements are true. So Jamal eats soup and Jamal eats salad with his meal. All right, so that's just a warning. In the mathematical framework, the word or could be true when both of the component statements are true. All right. The next compound statement is a tricky one. It is also one of the most important compound statements. It's called a conditional from P to Q. It's denoted with an arrow, and that arrow is pronounced if P, then Q. All right, so it's a statement that's true if it's never the case that P is true and Q is false. So that's describing the situation where the conditional statement would be false. Let's look at an example. This is an example I'm going to come back to many times. So my example is going to start with the two component statements, P being equal to the fridge breaks within a year of purchase, and Q, the repairs will be completed for free. And my conditional statement is going to be a warranty statement. And it says, if the fridge breaks within a year of purchase, then the repairs will be completed for free. Okay, so let's fill in together these four truth values for the conditional statement that, of course, rely on the truth or falsity of the component statements P and Q. Okay, so the first row of the truth table here is when P is true, the fridge does break within a year of purchase, and Q is also true, the repairs are completed for free. So in that case, where the fridge does break and the repairs are free, then the warranty statement, the conditional statement, is true. So that is a T value in the warranty statement, the conditional statement. In the second row of the truth table, we have that the P component statement is true, meaning that the fridge does break within a year of purchase. But the Q statement is false, meaning the repairs were not free. All right, that's a clear example of the warranty statement being false. It isn't true that if the fridge breaks, then the repairs are free because the fridge broke and the repairs were not free, as indicated by the statement Q being false. So that's the situation, the if part being true, the then part being false, that makes the conditional statement if P then Q false. The other two rows of the truth table here are when the if P is false. The P component statement is false in both of these. So what does that mean? That means that the fridge doesn't break within a year of purchase. So if the fridge doesn't break within a year of purchase, there are no repairs. So the warranty statement is automatically true if the fridge doesn't break. All right, so the P statement being false automatically gives us a true warranty statement. So those are both true values. So here's a case where this truth table definition of our conditional statement just requires some careful, slow thinking to get used to understand when the conditional statement is false. There's only one case of the 4 cases here where it's false, and in all other cases, it's true. Right? All right, conditional statements can be written down in many different ways. So here's a whole bunch of variations on the warranty statement. So our original warranty statement is if the fridge breaks within the year of purchase, then the repairs will be completed for free. I'm going to read through the first 2 of these aloud and then let you pause the video and read them to yourself. So the first one here is if the fridge breaks within a year of purchase, the repairs will be completed for free. That's just taking the word then out of the statement, but it's implied still. The other second example here is that the repairs will be completed for free if the fridge breaks within a year of purchase. All right. The third sentence here is the fridge breaks within a year of purchase only if the repairs will be completed for free. And I'll let you read the next one. And there's 4 more. Assuming that the fridge breaks within a year of purchase, then the repairs would be completed for free. And I'll let you read through the next 3 example statements here. These are 8 different ways of structuring a sentence that is encoding a conditional statement. All right? Okay. Biconditionals. So again, we're going to take 2 component statements, P and Q, and put them together in a biconditional. And the biconditional is denoted with this double-headed arrow, and that double-headed arrow is pronounced if and only if. So the P if and only if Q is the statement that's true if both P and Q are true, and it's true if both P and Q are false. And if P and Q have opposite truth values, then the biconditional statement is false. All right, so here's some examples. I walk around Bush Park if and only if it is Thursday. And that sentence is equivalent to saying it is Thursday if and only if I walk around Bush Park. So it doesn't matter if you have a biconditional, it doesn't matter which one is first and which one is second. The third example down there is I will pay for lunch if and only if you pay for dinner. So the truth of me paying for lunch, if the biconditional statement here is true, means that you're paying for dinner. And if you're paying for dinner, then I'm paying for lunch. All right. One last construction. This isn't exactly a compound statement, but it's an operation that you can apply to a simple statement, and that is to negate it. So the negation of a statement P is denoted with that little, almost like a minus sign with a little hook on the right side. It's the statement that is true if P is false and false if P is true. So negating a statement is changing its truth or falsity to false or true. So here's an example. It is not Thursday. So that's the negation of it is Thursday. And item number 2 is it is not the case that roses are red and violets are blue. So that is negating the conjunction roses are red and violets are blue. It is not the case that roses are red and violets are blue. So that's a pretty simple one. So P, if P happens to be true, then not P is false. And if P happens to be false, then not P is true. All right. Here's what we're heading towards, an example where we're asked to work with compound statements and determine the values of a truth table for a compound statement. So here is a complex compound statement. If it is not Tuesday, then Olivia is baking and Dante is gardening. So the component statements here are, I'm just going to call them S for it is Tuesday. B, Olivia is baking. And D, Dante is gardening. So in notation, I don't actually have the statement S as written in my compound statement. I have if it is not Tuesday. Oh, I have an if, so I have a conditional statement. So that if and the then here are encoded with the arrow. And it is not Tuesday is a negated S. And after the then, we have Olivia is baking and Dante is gardening. And that and is indicated with the wedge symbol here that looks like the letter A with the crossbar missing. All right, so the notation for the statement that we're interested in is not if not S, then BNT. And we're going to determine the truth and falsity of that compound statement. All right, here we go. Here is the truth table. And since I have three component statements, S, B, and D, my truth table just got a heck of a lot bigger because my truth table has to include all possibilities. So you'll notice that I have true, 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 false, true, false, true, true, false, false, true, 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 false, true, false, 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 true, false, and false, false, false. Those are the 8 possibilities for the true and false values of S, B, and D. All right, so let's start with the very first row of our truth table for our compound conditional statement. The first thing I'm going to do is I'm going to determine the truth or falsity of not S, and also determine the truth or falsity of B and D. And in the first row, S, B, and D are all true. So that means that not S is going to be false, and B and D will be true. In the second row of the truth table, S is true, B is false, and D is true. So not S is going to be false, and the conjunction B and D is going to be false because B happens to be false. And the conjunction is true if only if both of the two component pieces are true. Okay, so false and false for column 1 and column 2 in our truth table. All right, so we're going to continue that line of reasoning. Here in the next row of the truth table, S happens to be false. And that means that not S would be true. In the third row of the truth table here, T and T values for both B and D give us a conjunction that's true, and so on and so forth for the rest of the table. I'll let you think your way through each of these true and false values. So once I have the truth or falsity of the if part of my conditional and the then part of my conditional, I can now determine the truth or falsity of my conditional statement. And remember, the conditional statement, when I was describing it as if P, then Q, it's only false if the fridge breaks and the repairs are not free. So if I see a true in this column and false in this column, that's what I'm going to have a false for my conditional statement. So I can see a true in column 1 and a false in column 2 in the 4th row of the truth table. I can also see in the 7th and 8th row of the truth table a true in the if part of the conditional and false in the then. So that's also going to give us falses. So here are the values. So true, 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 that's where it's false. And then the remaining values are true, true, false, and false. So those last two values are false because the if part of the conditional is true, the fridge does break, but the consequent is false, meaning that repairs aren't free. So that's why those last two rows of the truth table are false. All right, we'll be working over some of the other examples like this in class. And for additional examples and explanations, please read sections 1.1 and 1.2 from our textbook. Thanks so much. Bye.